Is I'm audible?
Yes, sir.
Okay. Yeah. Now please copy this problem. Take this problem. The screen is visible. Give me confirmation. Yes, the screen is also visible. Yes, please copy this question and write the given data. See that the stresses induced at a critical point in a
No, sir.
machine component made of steel are as follows. So what are the given data? Given data. First one is sigma x is given. How much it is? 100 Newton per mm square. Then sigma y is given. How much? It is 40 Newton per mm square. And I'm audible. The PPT is also visible. Please, anyone give me confirmation.
Yes, sir.
Yes, sir.
Okay. Now sigma x is 100 Newton per mm square. Sigma y is 40 Newton per mm square. And tau xy is given 80 Newton per mm square. Right? Calculate. What we are going to calculate here? Factor of safety. The factor of safety is represented as what? Small n. Factor of safety is represented as small n. Then how to calculate factor of safety? By first one is maximum normal stress theory. And second one is maximum shear stress theory. Now take yield stress for the steel material. What is yield stress we represent as? Sigma y or sigma yt. Right? Sigma y or sigma yt. That is equal to how much? Yield stress is given 380 Newton per mm square. Right? These are the given data. Now we'll go for calculate the factor of safety. How to calculate factor of safety? The based on the two criteria. Take the first one. Based on two criteria, we go for calculate factor of safety. Take first bit A. Based on which theory? Based on maximum normal stress theory. Based on normal stress theory or physical stress theory. Right? Now how to calculate the factor of safety based on maximum normal stress theory? So we know that what is the failure criteria? Failure criteria or failure condition is, what is the equation? Failure condition is sigma 1 comma 2 that should be greater than or equal to sigma yt by n, right? Sigma yt by n. Further, this is the equation number 1. Sigma 1 comma 2 that should be greater than or equal to sigma yt by n. In this, if I want to calculate factor safety n, our aim is to calculate factor safety n. If I want to know n, I should know sigma 1, comma 2, which is the maximum value that we consider. And sigma yt I should know. Sigma yt already given in the problem itself, that is 380 Newton per mm square. Then how do you calculate sigma 1, comma 2? Where sigma 1, comma 2. Now, how do you calculate sigma 1, comma 2? Refer equation 2.34 and 2.35 from the design data handbook. From the design data handbook, sigma 1, comma 2 is equal to what? Sigma 1, comma 2 to that according to maximum normal stress theory. The failure criteria is sigma 1 should be greater than or equal to sigma yt by n. That part is equation number 1. Then from design data handbook, what is sigma 1 is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 whole square plus tau y square to the power of 1 by 2. This is equation number 2.33. 3 or 3, 4, please check. Yes. Now we know sigma x value is 100 Newton per mm square. Sigma y is 40. Right? The tau xy is 80. The substitute and calculate. Finally, we will get sigma 1 is 155.44 Newton per mm square. So substitute that value into the equation 1. Substitute that value into the equation 1. Sigma 1 we know that. Sigma yt also we know that. Then we go for calculate factor safety. Get how much factor safety you get. Please check. Write the formula, the substitution, then go for calculation. Check the answer whether it is right or wrong. Sorry, this is the equation 3, 4 or 3, 5. Yes, anybody is calculating? Just give me answer. Otherwise, I'll go for give the explanation. Just give me information. Anybody is calculating or not? Yes or no? Okay, see that based on the maximum normal stress theory, we'll get factor safety is 2.445. Similarly, go for based on the maximum shear stress theory. What is the failure condition for shear stress theory? The maximum shear stress induced tau 1, comma 2 that should be greater than or equal to tau allowable. Allowable shear stress. The allowable stress we can represent in terms of is always half of the allowable normal stress. The normal allowable stress is sigma yt by n. This will be the failure condition. This data, this formula is not available in your data handbook. You should remember. You should remember this failure condition for only maximum normal stress and shear stress. The whatever the design criteria, design equation that will get in the data handbook. Now in this, I want to calculate factor safety n. I should know what is the tau max. What is the tau max? From the design data handbook, equation number 2.37. Tau max is equal to, this is the equation, sigma x minus sigma y by 2 whole square plus tau y square whole to the power of 1 by 2. Then back substitute this value into the equation. Now finally we get The factor of safety is n is equal to 2.23. 2.2, 2.223. This is the way you have to calculate the factor of safety. Clear? Is any doubt? First read the problem once or twice, write the given data. After that, which is unknown data you have to calculate. Take that this heading based on that theory. Write the failure criteria for that corresponding theory. Then determine the unknown parameter. Then back substitute the main equation, we get the unknown value. Similarly, take this problem, take the screenshot of this. Will not go for solve this problem. Take the screenshot of this. A solid circular shaft is subjected to bending moment 40 kilonewton meter and torque of 10 kilonewton meter. The diameter of the shaft according to maximum principal stress theory, maximum shear stress theory, takes stress at elastic limit, means it is a yield stress. What is the yield stress here? Given 200 Newton per millimeter square. And factor of safety as 2. Now in the previous column, directly they given sigma x, sigma y, and tau xy. Right? And yield stress also given. But in this problem, sigma x, sigma y, and tau xy is not directly given. Then how do you calculate? See that from the what type of component is a circular shaft subjected to bending moment. Bending moment is given 40 kilonewton per to 40 kilonewton meter. From this, by applying pure bending moment equation, that is equation number 2.90, I think. MB by I is equal to sigma B by C is equal to E by R. From this, calculate the sigma B. The sigma B is what? Stress acting in what direction? X direction. That is the sigma x calculated from the bending moment. Next, from a torque of 10 kilonewton, the torque is given. From the torque, again apply a pure torsional equation. What is the pure torsional equation? Mt by J is equal to d theta by L. That is equal to tau by R. In directly take only the tau by R. From this, you go for calculate tau. What is tau equal to? Tau xy. Tau xy. Right? Tau xy. Now what is sigma y? Sigma y is 0. Right? Now sigma x will get sigma b is equal to sigma x. That will get in terms of diameter d. That is I is equal to 5 d to the power of 4. That is 64. Then tau is equal to tau xy. That is also will get in terms of d only. That is j is equal to 5 by 32 d to the power of 4. R is equal to d by 2. Then sigma y is 0. Then you go for apply the maximum principal stress theory, the condition, and maximum shear stress theory. Factor safety is already given, n is equal to 2. Sigma y t is also given, 200 meter per mm square. Then you calculate the diameter. Okay, based on principal stress theory and based on maximum shear stress theory. Clear? Or we'll try to solve in offline classes. This problem will solve in offline classes. Clear? That completes what failure theories. After the failure theories, one more. The last topic in this module is the stress concentration. Yeah, now the PPT is visible. Please give me confirmation.
Yes, sir.
Yeah, what is the heading here? What is the title of the PPT? The first slide in the PPT.
Stress concentration.
Stress concentration.
Yeah, stress concentration. So what do you mean by stress concentration? For a best example, okay, just I will switch on that video. I'll also give you some demo here. Yeah. So those who have the sheets, take the sheets. Now if you take the sheet. Now it's visible. See the camera, right? Give me confirmation. Is anyone can?
Visible, sir, visible.
Yes, sir.
Now I want to break this the sheet by applying a tensile load. If you have a sheet, please take the sheet and also try it. Try to break this sheet by applying a tensile load, not here, by applying a tensile load. Yes, sir. Please try it. This demonstration is very, very important. You know to understand the stress concentration, whatever stress concentration. Yes, anybody is trying to, if anybody tries to fail this sheet by applying a tensile load, see the how much load is applied here to break the sheet, right? Similarly, instead of that, if you go for take the one more sheet, submit it to a hole. Means what is the geometry is discontinuity. Earlier the sheet is there is no discontinuity in the geometry. There is no discontinuity in the geometry. The geometry is continuous. Then if you apply a load on the member, so more load is takes place to break the component. Similarly, take second one. The geometry is discontinuity. Here hole is there. Is a component subject to a hole, a flat plate subject to a hole. Then you can easily break the component. Why you can easily break the component? Why it is easy to break the component? See that the component is there in subject to a load. What happens here? The area is very less. The stress is will concentrated on very less area. The stress is very concentrated. Means the maximum stresses are induced. The accumulation or localization of the maximum stresses due to when irregularities or abrupt change in geometry. Then the maximum stress is concentrated at the where the area is less. Then the component will failure takes place. That is what intention we go for discuss here stress concentration. Yes. Now, what is the stress concentration? The next slide is visible. You can try it at your home. Take the two states. One is without surface irregularities, other one is with a surface irregularity with a hole. Then which will take the maximum load. If the geometry is continuous, it takes a more load to break the component. If the geometry is discontinuity, abrupt changes in cross section or irregularities are there, then it is easy to break. Means the maximum stresses are concentrated at particular location. Now, what is that stress concentration or also called as stress risers? How to define the accumulation or localization of maximum stresses due to what? Due to irregularities or abrupt change in geometry or abrupt change in cross section. That we call as a stress concentrated. I hope you understood what is the stress concentration. Stress is concentrated at particular location or particular point. That is called as a stress concentration. When the particular location stress is concentrated, whenever the abrupt change in geometry or irregularities that present in the geometry, then you can see the stress is concentrated. Right? Let's see that in the figure, this figure, you can see that there is the geometry is continuous here. There is no abrupt change in geometry. It's a rectangular plate. When you substitute a tensile stress, how the stress is distributed? Is stress is distributed normal to each other, and what is the stress line is parallel to each other, right? Parallel to each other. There is no discontinuity there. The stress is uniformly distributed over the component. If you take any irregularities contained in that component, take this sketch. You can see that a circular hole is there. So what happens due to circular hole? The stress will accumulate. Where the stress is accumulated here, the maximum stress is accumulated at the circumference of the circle at this where the cross-sectional area is less. The stress is accumulated. Where the stress is accumulated, why the stress is accumulated, you can see that if you draw the stress flow lines, if you draw a stress flow lines, earlier it is no irregularities, no abrupt change in geometry. There is a stress lines are parallel to each other. When here, due to the irregularities, due to the hole in the plate, what happens? Stresses are concentrated at this. The stress flow lines are not parallel to each other. That is what we call as a stress concentration. That is what the definition: accumulation or localization of maximum stresses due to irregularities or abrupt change in cross section. Similarly, take one more, the geometry. One more geometry is irregular geometry. It is sudden decrease in dimension. In the figure number, this figure C. The figure is what is highlighted here. That figure you can see here. What happens in this figure here? Suddenly, the diameter of the or the component decreases, or dimension of the component decreases. Now, here also the stress is accumulated here. When you subject it to load on the component, the maximum stress are accumulated at the sharp corner. This is called as a shoulder. This is what we call as a shoulder. This one is called as a cone, right? Now that is called as a stress concentration. Why do we need this irregular geometry? Means in order to do its function, the component will go for use a hole. For example, if you take a car body or a bus body or aeroplane body, intentionally we need a door and windows, right? The doors and windows are called as a stress risers because the geometry is not continuous. Geometry is abrupt change in geometry, right? That is called as the risers are that irregular. It is contained in the geometry. That is has to do its function. We want to avoid this, right? So then what are the irregularities are there? What are the discontinuities are there? The main cause of stress concentrations are some sort of irregularities. What are those irregularities? There are three types of irregularities. One is geometrical irregularities, means there is a sudden change in geometry. If it is decrease in dimension or increase in dimension, or there is any obstacle in the geometry, obstacles, it may be holes or grooves or cracks, keyways, right, notches or threads. Those are called as the geometrical discontinuities or irregularities, or it may be internal defects also. Second one is a load discontinuity. Load discontinuity means on one side, one component, one load is acting, tensile load. Other side is compressive load. Its magnitude may be changes, right? This is called as a load discontinuities. For example, if you go for a ride in a bike or a car on a rough road surfaces or a speed breaker, what happens? Speed breaker, the load is uniformly distributed on the component, on the speed breaker, or on the road surfaces, on the rough road surfaces, on the vehicle. No, sudden load is occurred here, right? Or sudden the load is varies. That is called the load discontinuities. It's not a uniform gradual load is occurred. Third one is material discontinuity. Means material discontinuity, all the component is not made up of a single material. It may be two or more material. Or if you want to, intention is to the geometry is not made up of single material. It may be two or more material, right? That's called the material discontinuity. Here we'll go for mainly discuss with geometrical discontinuities. This is the main reason why the stress concentration is occurred, right? Any doubt regarding stress concentration? Stress concentration of stress risers are accumulation or localization of the maximum stresses due to whenever the geometries irregularities are abrupt change in geometry. That is called stress concentration, right? Next. Now the next slide is visible. The heading is stress concentration factor. Just give me confirmation. Is anyone please give me confirmation?
Yes, sir. Visible, sir.
Now the stress concentration factor. Factor is nothing but what? Ratio. How do you represent here? K suffix sigma. So what is stress concentration factor? It is defined as the ratio of the maximum stress to the nominal stress. Now our intention is to calculate the maximum stress. What is the nominal stress? The nominal value. The nominal value that contained in the stresses induced in the material. That's called the nominal stresses. We'll go for purchase any component, take what will be the value of that product. This is a nominal value. This is a nominal value. Minimum value will product. That's called the minimum stress. Right? So that is the definition for stress concentration factor is the ratio of maximum stress to the nominal stress. That is a symbolically we can represent as K sigma is equal to sigma maximum by sigma nominal. That is for axial and bending load. So what it measures? It measures the stress concentration. How much stress is concentrated on the surface irregularity or geometrical irregularities in the component. How much maximum stresses are induced? That will be defined by the stress concentration factor. For axial or bending load, usually stress concentration factor is, that is an equation, mathematical representation is K sigma, that is for sigma max by sigma nominal. Where do you get? Refer the figure 4.7a and 4.7b. Clear? Then in this K sigma, directly we'll get from the data handbook, from the figure. Okay, that we'll discuss in next slide. Our aim is to determine what? Sigma maximum we want to determine. Then how do you calculate sigma nominal? The sigma nominal will calculate for axial load. Sigma nominal is equal to what? Force by area, cross-section area. Which cross-section area consider here? Where the minimum cross-section area is contained in the geometry, that we consider as a cross-section area. Then for bending load, what will be the nominal stress is sigma mb by I into C. How do you get this equation? You know the pure bending moment equation. mb by I is equal to sigma b by C is equal to E by R. Right? From this, what is sigma b is equal to? Sigma b is equal to mb by I into C. Right? Similarly, for torsional load, what we are when a body subject to twisting movement, then what will the stress concentration factor is the ratio of a maximum shear stress to the nominal shear stress. Then how do you calculate nominal shear stress? By applying a torsional equation, that is mt by j is equal to g theta by L is equal to tau by R. Here tau by R is nothing but R is nothing but what? C it is. That is tau nominal is equal to mt by j into C. C is what? Is the radius of the shaft, a distance from the central axis to the outer fiber. Right? Then these stress concentrations are also called as a theoretical stress concentration, not the actual one. So theoretically, you go for use a mathematical formula. That's why this stress concentration factor is called as what? Theoretical stress concentration factor. And that mainly depend upon the type of discontinuity. What is the type of discontinuity means? It may be a hole, it may be a groove, it may be a shoulder. That is called as the type of discontinuity. Size of discontinuity means what will be the size of that hole, diameter of the hole, right? What will be the sudden decrease in the diameter, the shoulder, right? That will be the size, the dimensions. But actual stress concentration factor is represented as K suffix sigma A or K suffix F into A. It is actually different from theoretical stress concentration factor. It mainly depends upon the type of material and type of load. That is the two other type of discontinuities. One is load discontinuity, other one is material discontinuity. Now the actual stress concentration factor is that is equal to 1 plus Q into K sigma minus 1, where K sigma is theoretical stress concentration factor. How to get this formula? Refer the figure 4.13, where Q is nothing but what? A notch sensitivity or index sensitivity. That mainly depends upon 10 minutes time is left. Once session is ended, again please rejoin the session. Yes. Now once the notch sensitivity or index sensitivity, it mainly depends upon the material and the type of loading. So how much sensitivity is the notch? If we use V notch or circular notch, how much is sensitivity? Okay, that depends upon the material and load. For ductile material, we will not consider this Q value. For brittle material, we consider Q value, because for ductile material, when you apply a load, it undergoes a ductile in nature. It undergoes a plastic state, from elastic state to plastic state. That will not consider notch sensitivity. For brittle material, we will go for consider the notch sensitivity means the brittle material not undergoes the plastic state or plastic region. Sudden failure occurred here. Without intimation, without giving information, the failure takes place. That is called as that metal is brittle material, right? There we use the knot sensitivity. That case is 30 sigma is critical stress concentration factor. From the figure, we'll refer it. That depends upon the type of load. Again, due to some network issue, so I'm not able to continuously touch here. Okay, now the PPT is visible. Give it confirmation. Am I audible?
Sir, voice breakup is there.
Just 1 minute. Yes, am I audible? Yeah, your internet connection is unstable.
No, sir.
Okay. So this is the what? The actual stress.
No, sir.
No, sir, not audible.
Not audible.
ವಾಯ್ಸ್ ಬ್ರೇಕ್ ಆಗ್ತಿದೆ ಸರ್.
Okay, 1 minute. Yes, now please check. Am I audible? Just give me confirmation. Am I audible? Does anyone give me confirmation? Am I audible? Does anyone give me confirmation? Am I audible?
Ah,
Yes, please check. Am I audible? Just give me anyone confirmation. Am I audible?
yes, sir. Audible, sir. Audible.
Yes,
Okay,
sir.
thank you. Again, due to some network issue, my internet is also not stable. Okay. Yeah, this is how you calculate the actual stress concentration factor by referring the figure
Sir, voice breakup is there, sir.
4.13. Okay. Next. Now, how do you reduce this stress concentration? Stress concentrated on the engineering material, because we need to, whatever the material have the geometrical rigidity should be there, it has to do its function, right? Then I would go for join the one component to another component with the help of bolts. Okay, we need the go for drill the component, right? How do you reduce this stress concentration? Yes, the slide is visible. Give me confirmation. The methods of reducing stress concentration or mitigation of stress concentration. Does anyone give me confirmation? Yes,
Yes,
please give me anyone confirmation. The slide is
Yes, sir.
visible. Okay. Now again, this all the things are available in your data handbook. Okay, by chapter number 4. Okay, the first one is the drilling additional hole. If you consider a plate with only one hole subject to external load, what happens? The stress is concentrated at where the cross section is less. There the stress is concentrated, right? Instead of using, again, if you go for stress lines, the stress is concentrated on the circumference of the hole here, where the area is less. Then how do you reduce, how do you make stressing not concentrated? Then instead of single hole, we go for do the multiple holes, a smaller diameter in the adjacent of the main hole. Then what happens? The stress flow lines is nearly parallel, but not exact parallel to each other, nearly parallel to each other. Again, stress will not concentrated here. It's the one. First one is drilling additional hole. Second one is using fillets instead of shoulders. If you consider a shaft, usually whenever the diameter is reduced here, from larger diameter, smaller diameter, what we can see here, you can see the shoulders, right? A sharp corners. Instead of going sharp corners, what we do, the engineers will go for give a fillets, right? Give a fillet. Instead of a sharp corners, we go for give a fillet, that is a circular arc there, right? That is the second method in order to reduce the stress concentration. Then third one, use of multiple notches. If you use only one notch here, then again the stress flow lines will concentrate at the tip of the notch, right? Instead of that, what we will go for, use a multiple notches. If you use the multiple notches from the measurement, see how the stress flow lines are there, right? This is the third method. First one, drilling additional hole. Second one is using fillet instead of shoulders. Third one, use of multiple notches. Fourth one is using large diameter of threaded length. As you know that bolts here, if you use this a poor one, if you take this one is the major diameter and minor diameter, see the stress will concentrated at the minor diameter. Instead of that, we'll go for use a stepped one, or else we'll go for the use the larger diameter in the threaded length. This is good one, good and preferred one. Then fifth one is a removal of unwanted material. What is the removal of unwanted material is, if you take a single groove here, instead of the single groove, if you go for enlarge this groove, then it will remove the unwanted the material. Then sixth one is combining grooves and fillets.